These are the notes for AP Calculus on the topic of inverse functions. So first we'll review some properties, some pre-calculus properties of inverse functions, and then we'll see how calculus relates to inverse functions. So inverse, remember in mathematics, another way of thinking about it is like it's a reverse. Or an inverse function is kind of like the undo button. It undoes or reverses what the original function does. The notation for it is, it looks like a little -1 is an exponent, but it doesn't really mean an exponent there. It means that's the inverse of the function f of x. So we've got three properties we're going to look at here, but let's see how that works using this specific set of inverse functions so we can kind of see why. So this is the graph of e to the x, the exponential function, and this is the graph of the natural log of x, g of x, which is the same as log base e. And whenever you have an exponential and a logarithmic function, if they have the same base, in this case e, they're going to be, if they're not shifted around or anything, they're going to be inverse functions of each other. You can see that with the graphs here. So let's take a look at our first property by just substituting in some specific numbers here. So something easy to substitute in for x here would be 0, right? And if we substitute e to the 0, well, that anything other than 0 to the 0 power is just 1. So the y value would be 1. And if we substitute in 1, we'd get e. So e to the first is e. If we substitute in 2, we'd get, for x, we'd get e squared. Then, let's see what happens if we substitute in 1, this y value, into the natural log of x. Well, the natural log of 1, what would that equal? When you have the natural log of 1, remember logarithms, you're looking for the exponent. That's saying e to what power equals 1? Well, that would be to the 0 power, so y would equal 0. When you substitute in, let's try substituting e. So if you substitute in e, natural log of e, that's saying e to what power, because it's log base e, equals e. Well, that would just be 1. If you substitute in e squared, the natural log of e squared, notice I'm using the y values here, well, that's saying e to what power equals e squared. Well, that would be 2. So notice what's happening with all of our points here. The x and y coordinates are just reversed. Okay? And that's essentially what this is saying. It undoes the inverse what the original function does. The original function takes 0, gives you 1. The inverse takes 1, gives you back 0. The original function takes 1, gives you e. The inverse takes e and gives you back 1. So what this is saying, it can be written either way. If you plug some x value into a function, in this case we plugged in 0, and then take that result, which was 1, and plug it back in the inverse, you get back what you start with. It also works the other way around. You could substitute in a value for x, like 1 into the inverse, and you get 0. Take that 0, plug it into the original function, and you get back 1. So this is basically saying they reverse each other. Or essentially, you can kind of almost see that they're basically canceling each other out, because they're the inverses of each other. Kind of like when you take the derivative of an integral using our second fundamental theorem of calculus, the same type of thing happens. Those are inverse functions, so they essentially cancel each other out. Okay, now let's take a look at the graphs for the second property. So the domain, remember, refers to all the possible x values of a function. So the domain on this one, notice you can substitute anything in for the exponent, for x. So the domain here would be from -infinity to infinity. And the range represents all the y values. So remember, an exponential graph, if it's not shifted around here, e to some power is always going to be positive. There's horizontal asymptote at y equals 0. So it never equals 0. It gets closer and closer to it. So the range would be 0 with parentheses because it never equals 0 to infinity. Now let's look at the domain and range for natural log of x. Here's the graph of a natural log. It goes through 1, 0, as we saw right here, whereas exponential goes through 0, 1. So the domain on this one, the x values, notice you have a vertical asymptote at x equals 0, so the x value never quite gets to 0, so it'd be 0 to infinity. And the range, notice it heads down to -infinity, and even though it grows very slowly, it does go to positive infinity. There is no horizontal asymptote here. So it is from -infinity to infinity. So notice, because the x and y's are reversed for every single point, that's what causes the domain, or the x values of f of x, to become the range, or the y values of the inverse. and the range of f of x, the y values, to become the x values or domain of the inverse. You can see that on these functions right here. Then our third property, this is the new one. This is where, well, we kind of already saw this first part of it. If the f of x, we're going to define f of x containing the point AB, then the inverse is going to contain the point BA. So you can say they're just reversed around. F contains the point 0, 1. The inverse contains the point 1, 0. F contains the point 1e. The inverse contains the point E1, and so on. But let's start to figure out what happens with calculus. Well, with the derivative, now that we've learned the derivatives of each of these functions, let's see what happens for the derivative. So the derivative, f prime of x of this one, well, we learned the derivative e to the x. That one stays the same, is just e to the x. So if you substitute in 0 into that, well, e to the 0, that's just 1. If you substitute in 1 into x, that gives you e. And you substitute in 2, it's e squared. So it looks identical to the y values because the derivative of e to the x is just e to the x. But now let's look at those corresponding points. We learned the derivative of natural log of x, g prime of x here. Remember the derivative of natural log of x is just 1 over x. So if we substitute in these x values, if we substitute in 1, we get 1 over 1 is 1. If we substitute in e for x, we get 1 over e into the derivative. If we substitute in e squared, we get 1 over e squared. So what is the relationship between our derivatives at these corresponding points? Well, it's hard to see with a 1, they look the same, but you can see with e to 1 over e and e squared to 1 over e squared, notice they just become reciprocals. It's just because the reciprocal of 1 is 1 that you don't see that on this first point. So that's what this is saying right here. The slope, which is another word for the derivative, of f at AB is the reciprocal of the slope of the inverse at BA. Another way to see why that would happen, just looking at our pre-calculus slope formula between 2 points, remember it's the difference of the y's over the difference of the x coordinates, right? But since an inverse function, the x and y's or domain and range are reversed, look at what's going to happen. If we switch the x's and y's, see how that's going to cause the slope to just be the reciprocal? That's what's happening here. So let's write this relationship in a more formal formula here. And oftentimes, to make it easier to work with, we'll define as 2 different functions, just like we did here. If f and g are inverse functions, and to be consistent, we're always going to call the point AB is on the graph of the function f, the original function. And that means, based on this property here, if AB is on the original function f, its inverse, which in this case is g, that means the point BA is on the graph of g. And I'm going to use that consistently. AB to represent the point on the original function, BA to represent the point on the inverse. Then what this tells you is the derivative of our inverse at this x value b is 1 over, or the reciprocal, which is what we just saw, of the derivative of the original function at a. The key is, notice these are not going to usually be the same unless you have a graph that goes through the point like 1, 1 or -2, -2, when you reverse the coordinates it's the same. Because notice our derivatives here, they weren't reciprocals at the same x value, were they? They were reciprocals at corresponding points. Okay? So that's what's happening right here. Corresponding points, the x value of g is b, and the x value of f is a. So that's where the reciprocal is. The most common mistake is students will forget that these are not the same value here. Okay? All right, so let's take a look at some examples, see how this works. Start off with the easier ones, go to the ones that are more challenging. So the functions f and g are differentiable. That just means you can find the derivatives of each of them. And it tells you f of g of x equals x for all x. Well, that means if you plug in some x value into g and then take that and plug in f, you get back what you started with. That's just another way of saying f and g are inverse functions. Then it tells you f of 2 is 10, f prime of 2 is 8. what are the values of g of 10 and g prime of 10? Okay, so let's take a look at the information we're given here. F of 2 is 10. Well, that means 210 is on f, right? And since we told us essentially that f and g are inverse functions, okay, so that's like our a and b, then that means when we flip it around, 10.2 is on its inverse, which is g. And if 10.2 is on g, that means g of 10 equals 2, which is what the first thing I asked for. Okay, so that's pre-calculus, just reversing the coordinates of the inverse functions. But for g prime of 10, that's like our b value. That's going to be 1 over f prime of a. Using the formula right here. And do we figure out what a is? Well, yeah, there's two ways of seeing it. Remember, this is the point AB that's on the original function. This is the point BA that's on the inverse. So a, either way, is 2. So f prime of 2. And then we're told f prime of 2 is 8 right here. So g prime of 10 would be 1 over 8. So you can see the slope of the original function at the point 210 is 8. The slope on the inverse at its corresponding point, 10.2, is the reciprocal 1/8. Okay. Then let's take a look at the next one. This says f is a differentiable function. Gives you f of 2 is 5, f of 5 is 14, f prime of 2 is negative 7, and f prime of 5 is negative 9. So we may not know where we're going to use that yet until we start solving this. So this one says we've got g as a differential function, and this time it's a little more clear. G of x equals, this is the inverse of f. So g, this is the notation for inverse, is the inverse of f. And this time they just flat out asked just for g prime of 5. Well, let's see what that is. Well, g prime of 5 would be 1 over f prime of a, right? Just using our formula here. So this is our b value. We're looking for a. So this time we don't know right away what a is. So what we can do to reason that out is, well, this is b, this is a. So we can say, all right, well, we know 5a, we don't know what a is, that's the point on g. Remember, we're always going to find ba to be the point on g. Well, if that's the point on g, that means since f and g are inverses, if we reverse that around, a5 is on f, the original function. Well, now let's take a look at all the information we're given here. Well, if a5 is on f, well, that means 5 is the y-coordinate, and we're looking for the x-coordinate. So let's look up here. Where's 5 the y-coordinate? And if you look right here, you can see there's where 5 is the y-coordinate. So that tells us we can see 2, 5 is on f. That means a is 2. So now we know, okay, well, this is 1 over f prime of 2. And we're told f prime of 2 right here is negative 7. So you get 1 over negative 7. Notice we didn't use f of 5 is 14 or f prime of 5 is negative 9. So those are kind of provided for the common mistakes oftentimes people will make. This one's provided if you don't flip the coordinates around. You might think a is 14. if you think that you're looking for where the x coordinate's 5 instead of where the y coordinate's 5. And this one's provided f prime of 5 if you forget, if you think this is a is going to be the same as b, if this is just going to be f prime of 5. So those are kind of red herrings to help you get the wrong answer if you don't know exactly what you're doing. So that's why we didn't use either one of those pieces of information. All right. So let's take a look at the next one here. It says, let f be the function defined by f of x equals e to the 3x minus x squared plus 5. Okay, so we're actually given the function this time, unlike the last two. And again, it says g of x equals This means the inverse of f. So again, this is telling us g is the inverse of f. And we're told g of 6 equals 0. What's the value of g prime of 6? All right, so let's start with what we're looking for. We're trying to find g prime of 6. But again, that's our b value there. And so we don't know a yet, so it'd be 1 over f prime of a. But notice what we're given is g of 6 is 0. So that tells us 6, 0 is on g. Well, this is our b value, and this is our a value, right? So actually we do, based on this point, know a is 0. So this is going to be 1 over f prime of 0. Well, in this case, though, we're not just given f prime of 0. We have to find it because we're given f of x. So we can say, okay, well, f prime of x would equal e to the 3x, the derivative here, using the chain rule. The e part stays the same, e to the 3x, times the derivative of the function inside, derivative of 3x is 3. So that'd be 3 to the 3x. And the derivative of negative x squared, negative 2x, using the power rule, and then the derivative of 5 is 0. And then we want f prime of 0, so you would just substitute in 0 into that for x. So it'd be 3e to the 3 times 0 minus 2 times 0. But that becomes e to the 0. E to the 0, remember, is just 1 minus 0, so you get 3. So f prime of 0 is 3. So g prime of 6 is 1 over f prime of 0 is 3, so 1 over 3. So 1/3. So the slope of f at 0 is 3. The slope of g at 6 is 1/3, the reciprocal at corresponding points. Because if 6, 0 is on g, 0, 6 is on f. So they're inverse functions. All right. Let's take a look at the next one. This is one where they give you the least amount of information. So we're given the function, natural log of x plus 5. And we're given, again, g is the inverse of f. What's the value of g prime of 8? Okay. So for g prime of 8, remember it's going to be 1 over f prime of a. That's our formula for inverse functions. Or again, this is the b value, and we don't know the a value. So we're going to first need to figure out what a is. Well, let's start with the fact that we know b is 8. So we can say 8a, we don't know what a is on g. Okay? Remember, we always say dA is the point on g. Well, if that's the point on g and g is the inverse of f, then what point has to be on f? Well, that would have to be a8. And if the point a8 is on f, what can we do? We're not given any points here to solve for a. Well, if we substitute this in right here, this point in, for your x and y, a and 8, we can see if we can solve for a. So this is like our y, right, f of x. So we'll plug in 8 there, substitute 8 for f of x for y, and a substitute in for x. So it'll be the natural log of a plus 5. Well, now we have something we can use to solve for a. So to solve this, you would just subtract the 5 from both sides. Gives you 8 minus 5 is 3, equals. And then to make this one easier to solve for a, remember natural log is a short way of writing log base e. And then we got a. So then now to solve this for a, to get it out of the logarithm there, we just have to switch it from logarithmic form to exponential form. So the base is e. The exponent, remember the log is equal to the exponent, so the exponent is 3, e to the 3rd, equals what's inside the log a. So now we know a is e cubed. So that's good. So now we can write, okay, well, we know this is 1 over f prime of e cubed. I know what a is. But we still need f prime of e cubed now, right? So we have to take the derivative of this. F prime of x. Well, we learned the derivative of natural log of x is 1 over x. The derivative of 5, a constant, is 0. And then if we substitute in e cubed into that, f prime of e cubed would be 1 over e cubed. So that's what goes here. So in this case, what's going to happen? We'll get 1 over e cubed. Well, that's like taking the reciprocal kind of twice there. So 1 divided by 1 over e cubed is the same as 1 times the reciprocal e cubed over 1. So notice we just get e cubed. It's not always going to equal a. That's a coincidence on this particular problem. But in this case, it does happen to be that. So that's what g prime of 8 is, just e cubed. Now, a lot of times they will use f and g because the notation is a little easier to work with. However, sometimes they won't. So this time they're giving the information in a table format. They give us the x-coordinates, f of x, and f prime of x, some different x values. And it just uses the inverse notation. So this is the inverse of f. And we want to write an equation for the tangent line tangent to the graph at x equals 1. Notice this is a graph of the inverse, not to the original function. So remember, what are the two things we need for the tangent line? Well, we need the point of tangency and the slope, right? But this time the point of tangency and slope are for the inverse rather than for the original function. So let's start with the fact that we know the x-coordinate of our point of tangency 1. So we can say, okay, well, that means 1, and that's our b value. A, we don't know what a is on our inverse function. Remember, we're always going to define BA to be consistent, to be the point on the inverse. Well, if that's the point on the inverse of f, what point would have to be on f? Well, that would mean a1, if we reverse the coordinates, x and y, has to be on the original function f. All right, so how can we find a? Well, let's look at our table. Notice we know the y-coordinate has to be 1. So let's take a look. Where is the y-coordinate, which is f of x right here, equal to 1? That'd be right there, and you can see then the x-coordinate is 3. So that shows us, okay, well, now we know 3, 1 is on f. But be careful. It's easy to forget to do this next step. You might think, well, there's our point of tangency, 3, 1. But that's the point that's on the original function f. We want the tangent line to the inverse. So if 3, 1 is on f, what's the corresponding point that has to be on the inverse of f? Well, if you flip it around, that'd be 1, 3 is on the inverse of f. And that is our point of tangency. Because remember, the x-coordinate had to be 1, right, not 3. So now we have our point of tangency. Then the next thing we need for the tangent line is the slope. That comes from the derivative. So normally in the formula we write g prime, but there's no g in this problem. So instead we're just writing this. So we want the slope, so f prime, the inverse, and we want the derivative at our point of tangency of 1. And remember, the formula is going to be 1 over f prime of a. Do we know what a is? Yes, we do. Here's b, here's a. Remember, a we figured out is 3. So this is our b, this is our a. And so we just need f prime of 3. Well, 1 over, what's f prime of 3? If we look at our table, when x is 3, f prime is negative 2. So negative 1/2 is our slope of our tangent line. So then we can write the tangent line is just y minus the y-coordinate is of our point of tangency is 3 equals the slope, negative 1/2, times x minus the x-coordinate of our point of tangency is 1. And that concludes the notes for AP Calculus on the topic of inverse functions.